Let's take a conductor AB in which a current I is flowing from A to B. The electric potential at point A is VA and at B it is VB. As the current is flowing from A to B, the voltage at A is greater than the voltage at B. The potential difference V between points A and B is expressed as V is equal to VA minus VB. Let this be equation 1. As V of A is always greater than V of B, V will always be greater than 0. Let the amount of charge flowing from point A to B be delta Q in the time interval delta t. Delta Q can be expressed as the product of I delta t. Let this be equation 2. The potential energy of the charge at the initial point A is delta QVA. The potential energy of the charge at point B is delta QVB. A change in potential energy between points A and B is expressed as delta U potential, which is equal to final potential energy minus initial potential energy, which is equal to delta Q into VB minus VA. From equation 1, we know that V is equal to VA minus VB. Therefore, VB minus VA is equal to minus V. Let this be equation 3. From equations 2 and 3, delta U potential is equal to minus I delta TV. Let this be equation 4. Since the value of delta U potential is negative, it is less than 0. The law of conservation of total energy states that the total amount of energy in an isolated system remains constant over a period of time. Applying the law of conservation of total energy between points A and B, since the potential energy of the charge is decreasing, its kinetic energy must increase. Therefore, an increase in kinetic energy K of the charges is expressed as delta K is equal to minus delta U potential. From equation 4, we can say that delta K is equal to minus of minus I delta TV. This implies that delta K is equal to I delta TV. Let this be equation 5. Since the value of delta K is positive, its value is greater than 0. If the charges move freely through the conductor, their kinetic energy should increase, and they should move with greater velocity. But we know that on an average, these charge carriers do not move with acceleration, but with a steady drift velocity. This is because the free electrons collide with the ions while in transit. Due to these collisions, the kinetic energy gained by the charges is transferred to the heavy ions. And these ions vibrate more vigorously, thereby heating up the conductor. The heat dissipated by the vibrating ions is represented by delta W. This delta W is nothing but the increase in the kinetic energy of the charged particles. Therefore, delta W is equal to delta K. From equation 5, we can say that the amount of energy dissipated is expressed as delta W is equal to I delta TV. Let this be equation 6. The energy dissipated per unit time is termed as the power dissipated and is represented by P. Therefore, we can write P is equal to delta W by delta T. Substituting the value of delta W from equation 6 in the above equation, we get P is equal to I delta TV by delta T. On further simplifying, we get P is equal to IV. Let this be equation 7. According to Ohm's law, we have V is equal to IR. On substituting the value of V from Ohm's law in equation 7, we get P is equal to I square R. Let this be equation 8. Ohm's law can be rewritten as I is equal to V by R. Substituting the value of I in equation 8, we get P is equal to V by R whole square into R. This implies that P is equal to V square by R. Let this be equation 9. P, which represents the power dissipated or lost, is also called ohmic loss in a conductor of resistance R carrying a current I. This dissipated power P is utilized to heat the filament of an electric bulb to incandescence and radiate heat and light energy. Power is supplied to this resistor by an external source such as an electric cell. Similarly, there is power loss when a current I is transmitted from the point of generation to the point of utilization through transmission cables. The distance between these 2 points is often very large. The transmission cables have a certain resistance due to which there is a huge power loss. Using equation 8, that is, P is equal to I square R, we can derive an expression to calculate the power loss due to resistance in the cables. Power loss in the cable PC is due to its resistance RC, which is expressed as PC is equal to I square RC. Let this be equation 10, where I is the current flowing through a cable. According to equation 7, P is equal to IV, where P is the power generated at source, V is the voltage generated, and I is the current flowing through the cable. Rearranging equation 7, we get I is equal to P by V. Let this be equation 11. Substituting equation 11 in 10, we get PC is equal to P by V whole square into RC. That is, PC is equal to P square by V square into RC. Let this be equation 12. This equation helps calculate the power loss PC due to the resistance RC in the transmission cable. In equation 12, we can say that the values of power P generated at source and the resistance RC of the cable are constants. Therefore, it implies that the power loss by the cable PC is inversely proportionate to the square of the voltage generated. Therefore, to minimize the power loss in transmission cables, the voltage of the power produced at the point of power generation is stepped up using a step-up transformer before it is transmitted. This very high voltage is converted to low voltage using a step-down transformer placed very near to the point of utilization of power.